Hi everyone, my name is Janica and I'm a Master of Research student from the School of Science and Health at Western Sydney University. I have an undergraduate degree in food science and am now undertaking a research project which aims to identify and characterise bioactive, aroma and flavour compounds in native Australian food plants. Before I go into too much detail, I thought I should explain a little on what food science actually is. In the words of Geoffrey Campbell Platt, President of the International Union for Food Science and Technology, food science is an applied scientific discipline in which the sustainability, quality, safety and security of food resources is managed and innovated according to the needs of society. Now, if that's still a little unclear, what that essentially breaks down to is a very large scientific discipline which encompasses a broad range of analytical and applied methods to innovate and manage food preservation. And if you're still a little unclear, I'll try and use something a bit more visual. So let's just imagine this muesli bar as the epitome of food science, okay? Now, have a think about how much thought went into the design of this wrapper and the creation of this wrapper. What ingredients were used in its formulation? How healthy or unhealthy might it be? And then on a deeper level, have a think about what are the components that make up each of these ingredients? Has any thought been put into how it might look, taste or smell? And then by what manufacturing processes would this bar have been made? Hopefully that helps to paint a picture on what food science is. Next, I will explain a little bit more on food chemistry and why I chose to study this topic, particularly in food science, for my project. Thank you. Food chemistry is a subdiscipline of food science which studies the chemical reactions that occur within food as it is processed, matured, or consumed. It looks specifically at optimizing reactions that are beneficial, such as the conversion of lactose to lactic acid in yogurt production, and minimizing those which are potentially harmful or undesired, such as the enzymatic browning or oxidation of apples when their flesh is exposed to air for prolonged periods of time. Flavour and fragrance analysis is one particular aspect of food chemistry that I'm most passionate about. It involves the characterisation of aromas and flavours in food products and how these profiles can be augmented to better suit the needs or wants of the target consumer. This could be as simple as inserting a vanilla fragrance or flavour within a cake or a drink. My passion for flavour and fragrance chemistry, I guess, stemmed from my love of food, and in particular, my love of eating, as you can see from my little Buddha belly over here. This love was developed and refined during the years I trained and worked as a chef, pastry chef and baker, but it wasn't until I came to university and studied food science that my mind and my passion for food really flourished. Most notable of my experiences is when I took an internship at a flavour and fragrance house, and here I saw the inner workings of how aroma and flavour profiles were developed in foods from start to finish. Following that, I did a research project in the third year of my undergrad degree in aroma and flavour profiles, and this furthered my skills within the area and made me realise how much I really loved the field. And it was from there that I decided to pursue postgraduate research in which I could apply this passion further. My current research project focuses on native Australian food plants found within the Darug Nation, such as these guys: lemon myrtle, native sarsaparilla, and sandpaper figs, and identifying what their bioactive properties, aroma, and flavour profiles might be. If you're wondering why I chose to study native bush foods, consider this. These foods sustained the Aborigine people for the best part of 40,000 years. Some are known to local elders to possess medicinal and other health-related benefits. But why have they not been integrated into the Australian diet? And why does a large proportion of the Australian society remain uneducated on how to process or consume them? These are questions I plan to address in my research field as it expands. To clarify some of the terminology used in my research question, bioactivity refers to the beneficial or harmful effect exhibited by a compound or substance in or on the body. This term is used interchangeably with functionality, in food, whilst aroma and flavour refer to the sensory characteristics of food, i.e. substances which emit a unique scent or exhibit a unique taste. The study of native Australian food plants is a relatively small research field, with most work in this field having been done by the Food Science and Technology Group at UNSW, and Food Science Australia, which is now part of the CSIRO Nutritional and Food Science Division, and of course their affiliates. In recent years, interest in Australian bush foods has re-emerged in the search for novel functional foods to incorporate into our diets. A study by Ahmed and Johnson in 2000 reviewed the horticultural potential of developing 14 native Australian bush foods into a viable niche food industry. This prompted a number of other studies which examined the phenolic properties of these foods, medicinal and health benefits these antioxidants may possess. And for those of you who don't know, phenols are an acidic and aromatic class of compound with antioxidant and ultraviolet or UV properties. Two of the more recent studies revealed that there was a stronger antioxidant and oxygen radical absorbance capacity in 12 native Australian fruits in comparison to blueberries. This included muntries, Illawarra plum, and Tasmanian pepperberry, in addition to a few others. This was mainly attributed to the greater abundance of anthocyanin-rich polyphenolic complexes, or groups of many phenols, mostly anthocyanins in this case, heaped together to make one massive compound in these fruits. Kakadu plums in particular had 6 times higher phenolic and antioxidant capabilities than blueberries, and were found to contain more vitamin C than most Australian citrus varieties. And why is all this important? Well, that was illustrated actually by Sakul Namrat et al. 2014, who investigated how well they could inhibit key enzymes associated with metabolic syndrome, which is a condition characterized by obesity, hypoglycemia, and hypertension. She studied 2 fruits in particular, Davidson's plum and quandong. What she found was that Davidson's plum effectively suppressed alpha-glucosidase and angiotensin I converting enzyme, whilst quandong was the most effective inhibitor of pancreatic lipase. In a further study, she found that quandong did display a superior ability to prevent stomach mucosa injury and significantly reduce hydrogen peroxide-induced death of hepatocellular carcinoma or HepG2 cells. In comparison, Davidson's plum only had comparable activity to that of blueberries, and no significant cytotoxicity towards non-transformed colon, mixed stomach, and intestinal cells. What we can essentially take away from this, though, is that although her results weren't as promising as expected, she focused on only 2 native fruits. Analyses of more bush foods may, however, yield more favourable results, and thus the potential of pharmaceutical applications in the future. So, how does my work fit into all of this? Well, my plan is to complete a more comprehensive review of Indigenous Australian food plants, including but not limited to native fruits. I plan to examine their bioactivity, aroma and flavour, and then depending on what compounds I find, I'll be able to check whether they are known or unknown through a review of literature and instrument libraries. If they are unknown, then great, I'll have the opportunity to publish in a high impact factor journal of the discovery of a new compound. If they are known, well, I would like to see whether they are valuable vitamin or mineral needed in high concentration in the Australian diet. This presents opportunities to integrate the bush food containing high concentrations of this particular compound of interest into a food product to be introduced to the domestic market. And the best part of this is that it will require recipe formulation and taste testing, so make sure you keep in touch. There has been little to no work done on the aroma and flavour identification in native Australian bush foods previously, so my hypotheses in this area are subjective and informed more so on my personal sensory perception of these foods and analytical analyses that I carried out. I predict that of the food plants I examine, most will possess a unique and relatively simple flavour and aroma profile based on sample evaluations I carried out at Murrumbidgee, which is a Darug information and cultural centre near Penrith, who are supplying the native bush foods I used in my study. I also envisage that these plants, particularly the fruits and leaves, will be rich in bioactive properties, particularly antioxidant and anti-inflammatory compounds, as shown in studies by Netzel et al. 2007 and Koznak et al. 2010 A and B. The main benefits I propose to achieve in my study are an increased awareness and understanding of native Australian food plants within our society. This may then promote respect and an opportunity for education about Aboriginal customs and traditions with regards to food culture. I see it as a great shame that with such an abundance of native foods, so much of the Australian population is ignorant to how to prepare and eat the food of their homeland. I hope this study can spur change in the way Australians think about Indigenous foods and hopefully allow them to become more integrated into our diet. Potential setbacks that I may encounter in this study include the capabilities of my research team. My primary supervisor has only recently joined Western Sydney University, so many experimental conditions and methods I will need to set up from scratch. Equipment availability may also prove to be another issue, so I may need to go to other campuses or research groups within or outside the university to complete my data collection and/or analyses. Time is also one of my biggest concerns, as this research has a potential to extend well past a PhD level project. Given that I have 1 year of pure research as part of this master's degree, I feel I will need to limit my sample selection to perhaps 5 or so native Australian food plants. I may also only be able to complete a few select bioactivity assays and then finish with aroma and flavour characterisation of my samples. Any product development or formal sensory evaluations will more than likely have to be incorporated into a future PhD. Originally, I envisaged that my methodology would be purely quantitative, such is the nature of applied science. But through this course and the power of collaborative learning, I've realised just how valuable qualitative writing can be. Yes, even in science. So my plan is now to incorporate a mixed methods approach, which draws upon the rich verbal knowledge I've gained from the Aborigine Darug elders, and discussing this in the context of scientific data and observations. For example, for hundreds of years, the Darug people have used lemon myrtle leaves as a treatment for conjunctivitis in children by boiling the leaves in water and placing them over their eyes. This may be linked to the high antibacterial and antifungal properties observed in lemon myrtle in a paper by Jones 2006. Currently, for my engagement unit, otherwise known as Experimental Design and Analysis, I'm doing a mini project on post-column derivatization, which we'll call PCD for short. And essentially this is an analytical technique involving a HPLC, which stands for high pressure liquid chromatography, and if you look to the right of this slide you can see a HPLC right there, in which a sample is prepared in solution, known as a solvent, and then filtered into a small sample vial. Now in this case we're using lemon myrtle and cinnamon myrtle leaves as our samples. These are then ground in a mortar and pestle, and we use 2 different solvents to make up our samples. So in this case we use methanol, which is a derivative of alcohol, and water. These were then prepared and then filtered using a syringe, and then we prepared 4 samples here. So we can see we have 2 samples of cinnamon and 2 samples of lemon myrtle, 1 in water and 1 in methanol. And these were then ready to be analysed on the HPLC. So an injection from each vial was taken and inserted into one side of a column, which separates the compounds in that sample to be collected from the other side of the column. A mixture of other solvents are used to help push the sample through the column and hold the compounds that separate out. Now, don't worry if all this isn't sort of making sense. We have a video in the next slide which I'll explain this in a bit more detail, and you'll be able to visualize all that I'm saying. How PCD comes into this is that at the exiting end of the column is a 3-piece frit that's fitted. This allows the flow of the solvent of the compounds to be split into a central and outer flow. The central flow is usually sent to a detector or sent to waste, while the outer flow is mixed with a radical made in solution which scavenges for a particular class of compounds, such as phenols or anti-inflammatories, which we explained what they were earlier. Once mixed with the radical, the outer flow is then sent back to a detector to detect how much phenolic or anti-inflammatory activity might be in each compound which elutes out. This allows us to see all of the compounds in each native Australian food plant, which of them have a particular bioactivity, and how potent that bioactivity is. This saves time because in knowing this, I would only collect compounds with bioactivity to identify and characterize and discard those without any. In this mini project, as I said, I'll be analysing lemon and cinnamon myrtle samples and subjecting them to 3 different radicals: DPPH, ABTS, and 2 reagent, all of which screened for antioxidant activity. Okay, so here we have our HPLC system. Now here's the screen where we can see the chromatograms from our mass spectrometer, which I'll explain a little more in detail, and the other chromatograms for the flows that are coming out which contain our compounds. So in the center of the view there we have a mass spectrometer. On the top we have a pump, and at the bottom we have a sample tray. And here we have 2 more pumps, a detector, and another chromatogram, and this is what we see, what's being reacted with the DPPH. Now, this mass spectrometer that you see, this is a device that actually smashes all the compounds into small, tiny pieces, and then those pieces are analysed on a detector, which essentially determines or helps us to determine what type of compound it might be. So the way that these compounds fracture out is in a unique way, so it'll only fracture out in a particular way, and that's linked to a library which helps us to identify the compounds. Now we're looking here at a pump and a detector for the DPPH, and here is the sample tray. So all the little vials that you saw we made earlier are kept in here under refrigeration at about 4 degrees Celsius. We can't really see them, so I'm sorry about that. But so they're injected, and then through this little device here, that's pumped straight into the column, which you see is there. Okay, and that's held in a solvent. And at the end of the column, you see the 3-piece frit that I discussed with you before. Now, the central flow of that frit is going into the mass spectrometer, which is smashing up the compounds, as we said before. And then, we'll focus back in, and then we go back. Now, the outer flow, we have 2 wires that are taking the outer flow to somewhere. One of those wires is taking it to this UV detector, so that'll determine what UV wavelength the compounds are coming out at. The other line is going to this T piece, so that you can see that square little design there. So that's mixing with the DPPH in there, and then another line is taking it to the detector. Now the DPPH is in that foil jar that you can see sort of in the right hand corner there. So we keep that because it is light sensitive, so that flows out from that little foil covered bottle and then into the T piece, mixes with the outer flow, and then goes into this detector. Okay, there's a close-up on the DPPH bottle. So it elutes as a purple coloured solution. And DPPH, just for those of you that don't know, stands for 2,2-diphenyl 1-picrohydrazole. Okay, wonderful. And now we'll go back to the chromatogram. And we can't see too much now, but anything that reacts with the DPPH will appear there as a valley, so the opposite of a peak. And then here we can see 4 different chromatograms. The top one there is the mass spec, so that's showing all the little peaks for the different fragments that have been fractured from a particular compound. The second chromatogram that you see here is from the central flow that goes into a detector, and then this here is from the outer flow that goes into a detector. Okay, and at the moment the fourth one here isn't being used, so we're not actually getting anything come through there. Thank you for listening. The main things that have changed since I first started this project are in the way that I write. I've always loved to write creatively, but that was drilled out of me very early on in my undergraduate degree, in favour of a style which was quite cold, sterile, highly technical, and to the point. But this should not be the case, irrespective of whatever discipline you're studying from. Your writing should have clarity, be easy to understand, and have flow. If you cannot explain your work to your family or your friends or your loved ones without them understanding, how can you justify yourself as a researcher or academic? The qualitative online lectures for Research Design 1 in particular played a big role in opening my mind to change the writing styles that I have and my speaking habits. The other major shift from what I initially perceived I would have been doing is actually working with my supervisor, believe it or not. After having numerous meetings with him, we were unfortunately unable to complete any work together in this part of the degree, due to time restrictions and the fact we had no lab set up for us to use as yet. This will of course change by the second year, and we will be working together more often. But in the interim, I've been working with a co-supervisor and his research team at the Parramatta North campus. Well, as my project has the capacity to be quite a large research program, the future work at this stage will depend on how much work I'm able to actually get done within the set time frame of this degree, and what my findings are. As it's too early at this stage to say what they might be, speculatively I can say that at least in terms of product development and sensory analysis of native Australian food plants will be more than likely on the agenda for future studies as part of my potential PhD rather than incorporated into my Masters. I'd like to take the time to thank you for watching this video and gaining some insights onto my project. If you have any questions you'd like to ask or feedback you'd like to leave, please do so in the discussion section on views. Otherwise, you can feel free to email me at j.rupesinghe@westernsydney.edu.au. Thank you, and I hope you all have a great week. And here are all the references I used in this presentation.